Nice. Okay. Yeah, so I was saying that okay, this is introduction. Let me call it introduction. Of course, this is covering advanced topics, hopefully more than what you have already seen in during your bachelor. Okay. But I mean, I will start from the very beginning. So introduction to statistics, and the outline of, I don't know if I have sent you or that, I don't know if Claudia sent you the outline of the course anyway. So the outline of the course is the following. So today we will start by talking about generic concept of probability, the different approaches, etc. So this is going to be like an introductory part. And I am going to be a little bit fast on that because I am assuming that you know most of the concepts. But of course, you are entitled to interrupt me at any stage. Okay, so don't think that your question is stupid or whatever. Just pose me any question at any moment. And so we are probably start today with the second topic called statistical tests. Okay, so maybe I will talk about this today, but I am maybe not finishing this second topic today. So between, tomorrow I will at some point start talking about parameter estimation. Okay, this is probably between today and tomorrow. And then I will talk about confidence intervals. Model selection. And finally, I will cover sampling methods. And I will be focusing on Monte Carlo methods. Okay. So this is more or less the 6 topics I have prepared of this course. And okay, the bibliography I have followed mostly the Cowan's book. So this guy is Glenn. I don't remember now if there are 2 N's. Maybe not. Okay, I will put 2 N's, but I am not sure about the 2 N's now. The Cowan's book, and the book is called Statistical Data Analysis. And so this is mostly about this book. I have seen other books, but occasionally, and I also have, prepared this course with materials coming from other lectures that I have followed during my career, and this is like private communication, etc. So I may not be allowed to give you those slides, but let me tell you that just with the Cowan, you're quite covered. Okay, so I will be following this book, not in the same order, but I'm taking some topics, but mainly from this book. Okay, good. So let us start then by the first topic. Let's see. So let us then, okay, change color, and then let us talk about random variables. I will I will be passing like a little bit fast on that, but I mean, of course, many of these things are very conceptual, and then you may interrupt me whenever you want. Okay, so when you say that a variable is random, so you say a variable is random because you actually are not sure about the result of that variable. You are measuring something in your experiment or your device, etc. But you don't know the value with complete certainty, right? So there is some notion of uncertainty here. So you're sort of uncertain about its value, okay? And and why is that? So you may essentially you have two different sources of randomness, no? So you have, for example, randomness. For example, you have the possibility that your measurement is not perfect. So you have imperfect measurement. Why? Because you cannot be sure that your conditions under which you measure are identical. So there is some environmental effects, etc. And this gives you some sort of randomness, right? But I mean, imagine that you have a very, completely controlled environment where no environmental effects, or you are in a vacuum, etc. So if conditions are perfect, then this sort of randomness would go away, of course, no? But then you have like an intrinsic randomness coming from quantum systems, okay? Because we know that quantum mechanics is intrinsically random, right? So even though you may have a completely controlled environment or experiment, then of course you will have this the decay of a particle, whatever. You actually are not really sure when the particle is going to decay next time, okay? Then how do we deal with random variables? I mean, we deal with probabilities, of course. So for example, you may have a random variable being the color of a ball, let's say. So you have a black box, let's say from black box. You have a black box, and then you pick a ball, and then you have three possibilities, I don't know, red, green, blue, whatever, okay? And then you try to cover this randomness with constructing a notion of probability. So the probability is something that you define with some axioms. And the axioms are very basic conditions. So you have the probability of an event AI. This should be larger or equal to 0. So you have another axiom, which is the union of, for example, A1 and A2. So imagine that A1 and A2 are the following. So this is P of A1, and this is, I don't know, let me put another color here. And this is P of A2. And then you have an intercept here, right? And then the probability of this is probability of 1 plus probability of 2 minus that intercept, right? And then this is the intercept here. And the third basic axiom is the fact that the sum of all probabilities should be 1. Okay. However, you have other useful like properties. You have the probability of A given B. What is that? It is the probability of the intercept region divided by the probability of B. So in a way, this is the probability of A given B is this sort of fraction, right? The fraction of B B in this case, which is intersecting with A at some point, no? And another notation for this, which is more commonly used, and this is what we are going to use mostly here, is this notation. So the intercept is also written like A comma B. And this guy here, this guy in the numerator here is also known as the joint probability, okay? The joint probability of A and B. Okay, so then what about this joint? So this joint, I mean, you can see it, what I will write, you can see it from this diagram here. It is the probability of A given B times the probability of B. I am just using the formula above. But it is also equivalent to the probability of B given A times the probability of A, right? And this thing is related to something called the product rule. Of course, I mean, from this, we will have more on that later, but of course, here, from this, you get this relation, which is nothing but the Bayes theorem, okay? But I will talk more on Bayes theorem later. But it is just coming out of the sum rule of probability. And the last property I wanted to mention is that the probability of A is the sum over B of the joint probability of A and B. Okay, some people call this the sum rule. And this is nothing but the marginalization of B, let's say. Over B. Marginalization over B. Okay. It's just that you need to sum out all possible values of B, and then you will get the probability of A. Okay, any questions so far? Right. Now let us talk about interpretation. Interpretation of probability. And then here, the classical interpretation is to interpret this as a notion of a relative frequency. Okay. And this is of course known as the frequentist approach. Okay. And in this approach, the probability of A is nothing but the limit when n goes to infinity of what? Of the, I don't know, there is a fraction here. This is the number of occurrences of A divided by the total number of measurements. Okay. And of course, this interpretation makes sense. Well, in a typical setup that, for example, you have a physical experiment like a collider, no, and then you know a priori, imagine ideally, you know that your conditions, you control them, and then on these ideal identical conditions, you repeat the experiment many times, and then it makes sense that you have your frequentist approach in this sort of system, in this sort of experiment, let's say. Okay. So this makes sense when you can reproduce your experiments, or repeat, more than reproduce, repeat the measurements. Okay. It makes less sense if you only have a 1-1 experiment, like you observe the universe. There is only one universe that we know or that we can measure. So you cannot repeat, you cannot have this notion of frequency because you don't have n universes to observe. You only have one. And so, like, formally, it makes less sense there because, I mean, the notion of probability there should be different, right? And that's why there is this second approach to probability, which is a subjective probability, which is nothing but the Bayesian approach. And here, what we are actually saying is we talk about the probabilities of some hypothesis, probability of some hypothesis. For example, my hypothesis A, I am attaching a certain probability, and it is like interpreted as a degree of belief that hypothesis A is true. And then why you say, okay, hypothesis A is random, why is random? And then that's why I need to associate a concept of probability to the hypothesis A. It is because I really don't know whether my hypothesis is going to be true or false. Okay, so that's why it's a random. It's a random concept, or a random, yeah, I can say concept. So for example, in the context of Bayesian, again, so here, when I say that, then I say, for example, A can be, for example, the hypothesis that a measurement will yield some particular result, no? Will yield some particular result. Whereas B will be the hypothesis that certain theory is true. My model, I have a new physics model or whatever explaining my experiment, and I will hypothesize that this model is true, so then I will make some tests, let's say. Okay, so I will give more concrete examples later on that. So again, depending on the question you pose, of course, you will have one approach or the other. And then depending on the question, formally speaking, of course, people then they do variations of that. But formally speaking, there are questions that you can immediately associate to one approach or the other. For example, if I tell you, what is the probability that an experiment will yield some result. I'm talking about data here, right? I'm talking about observables here. And then, is this a frequentist or a Bayesian question? Or maybe I should say, this is answered with a frequentist approach to probability, or with a Bayesian, or the Bayesian interpretation of probability? What do you think?
Depends on the experiment, maybe.
No, you are, whatever experiment you are measuring an observable, and I'm wondering, and this observable is the observable of let's say a random variable. Let's say I am measuring the transverse momentum in a collider, let's say, or I am measuring the gamma ray flux from some experiments in the sky. So this is a random variable here, and so what would that be? Would that be Bayesian?
Yes, it would be Bayesian.
Why?
I mean, because you will never be able to exactly reproduce the experiment.
No, but this is something that you assume, no? So, like in collider physics or in direct detection experiments of that matter, you are never able to reproduce exactly the same thing, and nonetheless, you assume that, and you continue your computation.
But at the end of the day, when it's reproducible, the Bayesian approach reduces to the frequentist approach.
Say it again, sorry.
That when you repeat it many times, the Bayesian approach should reduce to the frequentist approach.
No, I mean, not in the interpretation. Probably mathematically, this is, in some situations, this is true, but in interpretation, it's completely different. So anyway, here the correct answer is frequentist, because I am talking about an observable here. So I am talking about the probability of an observable. Instead of this question, then probably if I write the other question, then maybe it is clear. What is the probability that, I don't know, the mass of the Higgs is in some interval? So here, mass of the Higgs is something that you don't observe in an experiment. Mass of the Higgs is a parameter that is defining, it is your hypothesis. I have the hypothesis that the mass of the Higgs is 140, let's say. Is this hypothesis true or false? By looking at the data, right? There is no hypothesis in the first question. There is just, or the hypothesis is exactly the observable, okay? So that's why I meant that this would be a Bayesian question. Okay. I'm not talking about the fact of in practice you cannot reproduce the experiment identical, etc. This is another question. Okay. And I am also acknowledging the fact that if you repeat the experiment an infinite amount of times, then mathematically the two results will be the same. And you will see that later. But while mathematically being the same doesn't mean that the object that you get, this number, is interpreted in the same way. So you can interpret these numbers in two ways. Okay. Then is it clear, or you don't agree completely on that? or maybe we can discuss later if you still have doubts on this. Any other questions so far? Okay. Then let us talk briefly about the probability functions. Probability functions, for example, I have first example of a continuous random variable. Oops. Random variable. So here, the probability of observing this variable x here in an interval which is, let me say that, an infinitesimal interval, x and x plus dx. And this is given by the PDF probability density function. So the probability of x being in this interval is just given by this, okay? And of course, this is should have one of the axioms of probability. The integral of this should be 1. And I can do the same for a discrete variable. For example, I can think of a variable being just the natural numbers. And here we talk instead about probability mass function. And then just, of course, you obey the same condition. Instead of the probability density function, you have a probability mass function. It's just the nature of the random variable. But then there are many useful functions on that. And I am now referring to, again, continuous variables. I will talk about the cumulative distribution function. CDF, sometimes it's called. And this is just the integral from minus infinity, or the domain, let's say, of the variable to some value x dx. Okay. And what is this? It is just it's just a probability for the value to take a value less than x. Okay. So typically, if I don't know, if f is something like that, then when you compute the cumulative, this is typically something like that, where this is 1. You are just integrating, and then you just accumulate the values, right? So there are several properties of properties characterizing the PDFs, etc. Some properties. And one of the properties is called the quantile of order alpha. And this is just the value x equal x alpha, such that the cumulative at this value is equal to alpha, right? So in the above plot, if I plot again f, here it would be the value such that the cumulative is alpha, right? So this is the quantile. And the median is another useful property. So the median is just the value or the quantile when alpha is 0.5. Okay. And in a way, this is just, of course, so there are equal probability for x being smaller than this x alpha and for x being larger than x alpha. Okay. This is what the median is defined. So where the probability mass or is equally to the left and to the right of that value. Then there is the mode, right? And the mode is just, this is just the R max. I mean, the value of x that maximizes f of x. Right? And then, for example, you have here f of x, and this will be the mode here. But then this is this is a simple example, but then there are more complicated examples where you have some behavior like this. And when you have behaviors like this, we say that this PDF is multimodal. It's multimodal because you have many modes. One of the modes may be the largest mode, so like the global maximum, but you may have several of it. And then a very, very useful property is the mean. So you have the mean of x, or it is the same to say the expectation value of x, or it is the same to say the first moment of f of x. It is exactly the same thing, and I call it mu, the expectation value of x, which is nothing but the integral of x weighted by its PDF, right? And this is arguably the most important, like, use of a PDF, no? The most typical use of a PDF. And what it does is to tell you, it's like a measure of where x is typically lying, no? It's typically observed. This is what it gives you, more or less. But then, and now that we talk about moments, then you can go to the second moment, which is the variance. It's identical to say the second moment of its PDF. And in the literature, so you typically parameterize it with this sigma square, which is the same as the variance of x, or the expectation value of x minus mu squared. Okay. So, I mean, it is just the integral of this quantity weighted by f, the integral from minus infinity to infinity. For example, I mean, and then another property of that, if I like compute what is this, so let me like develop this expectation value here. So I will just like compute the square, etc. So this is the expectation value of x squared minus 2 mu expectation value of x plus mu squared. Why is that? Because the expectation value of mu is mu. Because mu is not a random variable, mu is a deterministic quantity. So when you integrate, you get mu. Okay, is that clear? And then I substitute here, this guy here, I substitute it with the first moment, and this is just this expression, okay? And this is just a measure of how like widely X is spread around the mean. Okay. So this is the variance, and then let me just give you two more properties, like other higher moments that you may use at some point. So one of them is the skewness, and the skewness is the expectation value of X minus mu over sigma squared. So the skewness is what is this talking you about? This is like a measure of some like a degree of asymmetry. Let me put it like that. Of asymmetry of the distribution function. And then the other moment, and I will stop here, is the kurtosis, which is the fourth moment.
Sorry, Brian.
Yeah.
In the skewness, should the power be to the third, maybe?
Yeah. Thanks a lot. And the kurtosis is telling you something about the tailoredness of the distribution. This can characterize the outliers, etc. Okay, so those are typical moments that you need. Of course, the first two moments are the one that we typically use, but I mean, at some point, it is also useful to have these other higher moments. So now let us talk about what would be the PDF of a function of X. So the PDF of A of X, this is what I'm writing here. It is computed by the requirement that, I mean, you need to require that. So you go to the definition of what a PDF is, be the same as the probability of X being in the interval, the infinitesimal interval. So if you compute this requirement, then you get the result. So this is if I call this G of X the PDF of X, and G of A the PDF of A. So G of A is nothing but F. Yeah, maybe I can put here an F as before of X of A multiplied by the Jacobian, right? And this is the way you compute the probabilities of functions of random variables. Okay, just compute the Jacobian. If of course if this is multivariate, then the Jacobian is a matrix, etc. So you know, that is generalized in a straightforward way. So another thing is what is the joint PDF? So imagine you have two variables. I will write the joint like this. And then I can have the marginal as I was writing before. Or I can have, so this is the marginal as before. And I can have, for example, the conditional, let's say. So I can have P of y given x. This is just this joint divided by f of x. But who is f of x is just the marginal, right? So conditional. And in this very same way, you can like work with the joint probabilities of, I don't know, m random variables. Then I will talk about the covariance of two random variables. And the covariance is just a generalization of the variance. So this is the expectation value of what? Of x minus mu x. So mu x is just the mean of x times y minus mu y. And if you like develop the product, etc., so you open it and then you get, this is expectation of x times y minus mu of x, mu of y. And then you see that this is the generalization of the expression that I was writing before. Okay. No, just to be clear. So this expectation, what is this? It's just the integral over the two variables of the product times the joint. Okay, minus the same thing. All good? Fine. If there is no questions now, I continue. So I can talk about useful probability distributions. So those are probability distributions that you typically encounter when you do data analysis, when you do physics, etc. And what would be the first, like the most simple random variable that you can think of?
Gaussian.
No. Gaussian. It is a very typical, but it's not the Gaussian is a random variable, which is I mean, this is describing continuous random variables. But what about a binary variable? This is even simpler, right? So binary variable can just take two arguments, two values. Okay. I hope you agree that this is simpler than a Gaussian. Right. So what is the distribution function of a binary variable? So in order to do that, you say, okay, let me define what is the probability for x being equal to 1. And I just put it mu. Of course, if this variable is binary, then the probability of x equals 0 is 1 minus mu, because I need to respect the axiom. And then the probability mass function describing a binary variable is the Bernoulli distribution. And the Bernoulli distribution is the following. Has the following form. When I have this notation, this conditional is, I mean, the nomenclature here is that what is at the left of the pipe is the random variable. What is at the right of the pipe is a deterministic parameter defining the distribution of the random variable. Okay. Then the Bernoulli distribution is It's just this 1 minus mu 1 minus x. Okay. And if x is equal 1, then you get mu. If x is equal 0, you get 1 minus mu, which is what you need to get. Okay. So what is the mean of this? The mean is just, I mean, how you compute it. No, you know the result, but I mean, the way to compute this is just you sum over all possible values of your random variable, and you have this. And when you compute this, of course, you get mu. Right. And if you compute the variance, given the formula I gave you above, you get mu times 1 minus mu. So it is straightforward to do it. Okay. Okay, that was arguably the simplest random variable that you can think of. And now remaining on discrete variables as this one, the generalization of that would be like a categorical variables, which are variables where now x can not only have two values, but you can have many values, like 1, 2, I don't know, k values, or a, b, c, or whatever you wanna put here, right? And then how do you work with that? There is a common parameterization of a categorical variable, which is very practical, which is depending on the literature, it is called the so-called 1 to k coding scheme. But the more fashion name for that, mainly among machine learning practitioners, is one-hot encoding. And this is nothing but the following. So you promote x to be a vector, a binary vector. So this is a binary vector. Then let me put it like this. So you have k entries of this vector, and each of the entries is a binary number, either 0 or 1. Okay, this is what I mean by this notation. And then, for example, imagine that you have 3 categories. And then imagine that my variable is equal to, I mean, x can have 0, 1, 2, let's say. These are the 3 values that it can have, and then it has 2. I mean, the value is 2. Then the way to represent this in the 1 to k coding scheme, then this is equivalent to write 0, 0, 1. And if x would be equal 0, then it would be 1, 0, 0. I mean, it's like you put everywhere 0 except in the position corresponding to the category. Okay. So this is the 1 to k scheme, or the one-hot encoding, if you read it in the machine learning literature here. And then the way to deal with this type of variables is just that, okay, you have each category or each class. This is also called class. K has an associated probability mu k. Okay, so you have that the probability of xk to be equal 1 is mu k. Okay. Then following this, you get the PMF of this sort of variable. I mean, again, here you have many names, sorry, many names in the literature. I am calling it generalized Bernoulli. And the generalized Bernoulli is the following. So you have, of course, that the parameters of the generalized Bernoulli are now a vector of parameters, no? One for each class. This is the product over K of mu K to the xk. And note that you can recover here the Bernoulli distribution if you have two classes, because then you have like mu to the x, which is the only value you have, times the second class. But the second class you are obliged to have 1 minus mu, and then you have 1 minus x. Okay, so this is a generalization of the Bernoulli. And then, okay, in the example where this random variable in the one-hot encoding is the second class, and then if it is the second class, then this is mu1 to the 0, mu2, mu2 to the 1, mu3 to 0. So this is just mu2, which is what you need to reproduce. Okay. So the expectation value of a categorical variable is, of course, mu. And then there is also an expression for variance, and if I encourage you to obtain it. Anyway, so very related to the Bernoulli distribution. It is called the binomial distribution. So what is the binomial distribution? Is the probability of having n successes, and I define a success by x being equal to 1 in capital N trials. So this is what defines a binomial distribution. So I write it here. It is, of course, a random variable given by two parameters, the probability of x equal 1 and the number of trials. No, this is the extra parameter defining the distribution, and this is just the binomial coefficient, and that's why this is the binomial distribution of this. Okay. So this is the Bernoulli, sorry, the binomial distribution, and the generalization is a multinomial distribution. So again, the probability of having n successes of n trials, where a success now is referred to the value of a categorical variables with more than two classes. And the multinomial distribution then is characterizing this vector of n, because you now are describing successes of all the classes given by these parameters, and this is just factorial of n, n1, etc., n k of what? Of mu1 n1, mu2 n2, etc., mu k nk. Okay. Note, by the way, that many people, Bernoulli is like some term that you hear much less than a binomial distribution in physics. But in many occasions, I just realized that when they say binomial, they wanted to say Bernoulli because they are putting binomial where the number of trials is equal to 1. And if the number of trials is equal to 1, binomial is the same as Bernoulli, right? So, but this is just the jargon that we use in physics. Sometimes it's like a abuse of the concept, let's say. But yeah, this is just to know this. And another very useful, very useful, mainly in physics, probability distribution is the Poisson distribution, and is describing a random variable which is a natural number. So the Poisson distribution is given by only one parameter, lambda. So this is lambda to the n, e to the minus lambda divided by n factorial. And this is a real number, lambda. This parameter is a real parameter. And it is simple, and actually the expectation value of n, I mean the mean, is equal to the variance. And they are both equal to lambda. And finally, the Gaussian. Or normal distribution. And this is just describing now a real parameter. I'm just writing it here, but I mean, you of course know the shape of the distribution. E to the minus x minus mu, like this. Whereas in this is for the univariate case, but in the multivariate case, it is something that is very used in data analysis. So imagine that the dimension of x is just d, okay? Then the multivariate normal distribution of x given some vector of means and some covariance matrix is just 1 over 2 pi d halves 1 over the determinant of the covariance matrix, I mean the square root of it, times the exponential of minus 1/2 of x minus mu transpose the inverse of the covariance matrix times x minus mu. Okay? And this is the covariance matrix. So you may be already familiarized with this expression, and then I will finish here because as the only example I will put now of a continuous random variable being the most important distribution, and the importance of this distribution is coming because of the central limit theorem. So there are like two ways people phrase this, but I will rephrase it in the following way. So it is the sum, is referring to the sum of n independent variables, random variables, of course, xi. We can have whatever distribution, each of them, but they are characterized by the mean mu I and variances sigma I square. Okay, I'm just writing it here because it is important, but otherwise unspecified PDF. So one can be I don't know, log normal, the other can be whatever other thing, etc. Then this sum will have a distribution that converges in this limit of n going to infinity to a Gaussian. to a Gaussian with mean given by the sum of the means and a variance given by the sum of the variances, okay? I'm not going to prove this theorem. This is proof out everywhere, and in particular, you can refer to the proof of it. It's chapter 10 in the book of Cowan. But this is the reason why Gaussian distribution is so important, right, in statistics, because, I mean, if you have an infinite, a large number of measurements, then essentially the Gaussian approximation may be very reasonable. Just there is something, there are many in the proof, etc. There are many like subtleties here, but just need to watch out, like when you are away from the center of the Gaussian, it may not be that Gaussian if the underlying distributions of X are quite non-Gaussian, okay? So what I'm saying is this is a theorem working mostly at the center of the distribution, but then when you really get far from the center, then if the distributions of these other random variables that you are summing or averaging, I mean, this can be also rephrased in average. If these variables are really non-Gaussian, then you may not have a perfect Gaussianity there, okay? And this is because, I mean, you're lacking of statistics, of course. Okay, so I think I have finished with the first topic. Is there any question so far?
Yes, I have one.
Yeah, go for it.
So when we define the functions of random variables, I think it was
Yeah.
before. Yes. So here, if we say that, yeah, A is a function of X, then the probability of X shouldn't be, the X's in the probability shouldn't be bounded, like from X, which is the value of A of X equal to A prime, to that X, which is A of X equals to A prime plus D A prime.
I didn't get the question, but I mean, so the relation between A and X is here, no?
Yes.
So I mean, this is where, I mean, the whole right-hand side should be given in terms of A, so that's why I put.
Okay, but the previous relation, is it?
The previous relation?
One? Yeah.
What happened with the previous relation? So it is like, yeah, there is like a drawing at some point that you made. That you may like do, so something like this. So imagine that this is A of X, no? And then like if you were talking about this interval, this is corresponding to this interval here.
Right.
Yeah. And so I am saying that the probability of A to be in this interval is the same as the probability of X to be in this interval. No?
Okay, maybe it's the notation. Okay, yeah. Oh, I agree with that.
Yeah, probably it's a matter of notation. So sorry if
okay.
it is not. Yeah, but we can discuss later. Yeah. Yeah. Thanks. Any other question before going to the second part? Okay. Fine. Let me then. go to the second part. Maybe since the second part is a bit more concepts, etc. If I give you 5 minutes and then we come back at what is 9 plus 5? We come back at 14 past. Okay. We'll just,
okay, sounds great.
Yeah. Okay. So I will reconnect on 14. I mean, I am not going away. I mean, just stopping the video, but let us reconvene at 14 past.